This lesson focuses on using the SUVAT equations. And the SUVAT equations are four equations that we need to be able to use, and they're for uniformly accelerated motion. Now, it's very important that you understand what that means. Uniformly accelerated means it under a constant acceleration. If the acceleration changes, you cannot use these SUVAT equations. The other thing is that you cannot or don't use these if there's no acceleration. This is only for objects that are acceleration. So if we want to find, for example, the distance an object travels while it's accelerating, we cannot use speed equals distance over time because our speed isn't constant, so we have to dig a little deeper. And they're called the SUVAT equations because we focus on these five quantities. S stands for displacement. And obviously that is measured in meters. U stands for initial velocity. And of course, normally we would do this as a small u, rather than the bigger one that's represented here. Initial velocity in meters per second. V is final velocity, also in meters per second. A, and again, it's a small a if you're representing it in equations, stands for acceleration in meters per second squared. And t, again, a small t, is time in seconds. And we basically just use these quantities and their associated equations with problems. And when we do a problem with this, what we want to do is identify what the problem gives us of these five quantities, which of those are given to us by the question, and then which ones do we need to find. And the equations then will help us find that missing quantity. Our first equation is derived in this way. So we know that velocity is displacement over time, and therefore displacement is velocity times time. But what if the velocity is changing? So if we look at this graph here, we can see that the velocity changes very regularly from u to v. What we can do in order to find the displacement is to say, okay, we can use the average velocity. The u is the starting velocity, v is the final, so our average velocity then would be u plus v over 2. And since displacement is velocity times time, we can say s then is equal to u plus v over 2 on t. And that is our first SUVAT equation. As an extra exercise, what you could say is, okay, this is a velocity time graph. Our displacement should be the area under this graph. So you could say, okay, the A here is a rectangle, so its area would be t times u, and B is a triangle, and its area would be half t times the difference between v and u. And if you add those together, you should find that you end up with the same equation. Equation number 2 comes from GCSE. We know that acceleration is the change in velocity over time. So the final velocity minus the initial velocity over time. And if we cross multiply and rearrange that, we get v minus u is equal to at, or v is equal to u plus at. That is number 2. For number 3, we have to do a little algebra. Now, you do not actually need to be able to derive this. If you look back at the specification point, you'll see it says use these equations. And these 4 equations are given to you in the data book that comes along with your exam. But with A-level, the expectation is that your algebra is very good, and that your familiarity with equations is very good, and that you are able to confidently substitute one equation into the other. So practicing deriving these gives you an idea of what the expectation might be. So what we're going to do is we're going to substitute one into the other. So we're going to get s is equal to half. And I'll do this nice and slowly. Okay. If we work on that a little, we should see that we get step by step, that equals multiplying in the t, giving us, finally, and that is number 3. Number 4. This one is slightly more complicated in its algebra. So what we're going to do is we're going to rearrange equation 2, which was v equals u plus at, and solve it for t. So t equals v minus u over a, and then we're going to substitute that into our original equation 1 given here. We're going to replace that t with v minus u over a, and then just multiply it out. So what you can do is you can try it yourself, pause this video, try it, and then come back and you can check out my working of it. I'll speed up the video so it goes a bit faster, and you can just check that you've done the same thing. And that is our 4th SUVAT equation. With these 4 equations, you should be able to solve any problem involving uniformly accelerating objects, so objects that are accelerating at a constant rate. You just have to identify, again, what you're given in the question, what you need, and then pick the appropriate equation. When you do this practice initially, keep the equation sheet that is given in the specification next to you, and you can use that to help you identify which equation to use. As you become more familiar with it, it will become much easier, and they'll be in your head, and you'll just be able to scroll through them, tuck, 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 and find which equation you need to use. Let's try some example problems. Okay, question 1, a cheetah accelerates, increasing its velocity from 10 meters per second to 28 meters per second during the final stages of a hunt. If it accelerates in 4 seconds, how far does the cheetah travel in this time? Certainly when you're starting out, the best thing to do is to do what I've just done, is highlight the numbers that you're given, and then try and identify which of our SUVAT, S-U-V-A-T, are these. So obviously 4 seconds is t. It goes from 10 meters per second to 28. So 10 is our u and 28 is our v. And we want how far. So from the language, you have to pick out what it is that you're looking for. So you can do it like this in the title. Another way of doing it is to write your SUVAT like this, down along the side, and then write in the numbers. Again, when you're starting, you might find this very useful, because it lays them out very clearly for you. We're not interested in acceleration here, so we're just looking for that. After a while, you get speedier. I find, personally, that the highlighting and the labeling above the question is just more straightforward and speeds up the process. Okay, so now we think we have u, v, t, and we want s. So we need an equation which have these 4 things in it, or we might need to use 2 equations and work our way through the problem. So what you can do here is, we don't have acceleration. If we think, okay, what am I going to do to find the s, the equations that have s in them, s equals ut plus a half a t squared, that's going to need a. V squared equals u squared plus 2as, again that needs a. We could find a, but remember we do have an equation with these in it. S is equal to u plus v over 2 on t. So we're going to use that one. And then all we have to do is put in the numbers. And you get 76 meters. This question is based on an actual news report that I saw, it must be a couple of years ago now. A man is jogging when chased by a rabbit squirrel. The squirrel in question was not a rabbit squirrel, it was actually a baby squirrel. And the police were called to deal with the squirrel. But anyway, he accelerates at 2 meters per second for 3 seconds. So let's start doing our highlighting. What is the final velocity of the man if his initial velocity was 4 meters per second? So that's our u, that's our a, t, and we want the final velocity, which is v. So again, we need something that has v, u, a, and t. in it. And you look or think through your SUVAT equations and you say, right, V is equal to U plus AT. And so 4 plus 2 times 3, very straightforward, 10 meters per second. Number 3, and again, feel free to pause this video at any point, work through the question yourself, and then you can just check your answer at the end. So a coin is thrown vertically downwards from a skyscraper. If the velocity of the coin is 40 meters per second after 2 seconds, what velocity was it thrown at? The acceleration due to gravity is 9.81. So let's start our labeling. The velocity of the coin after 2 seconds, so that's its final velocity, that is its time, and that's its acceleration. What was it thrown at? We need U. So again, we've got V, A, T, and we're looking for U. Seems familiar. V is equal to U plus AT. And what I would recommend you do, rather than rearranging the equation, this is an unusual thing. Obviously, we like people to be able to be skilled at rearranging equations. But when it comes to exams, there's usually a mark allocated for correct substitution. So if you just take the numbers from the question and put them in the right place in the unrearranged equation, you will get a mark even if you go on to make a mistake in the calculation. However, if you rearrange first and make a mistake in the rearrangement, then put the numbers in, you will not get that first mark. So it's better overall, just to be sure, to just substitute first, rearrange after. So now we've put our numbers in, we are trying to find U, and we can just carry on. And I'm doing this step by step so that you can see exactly how the rearranging is going. If, of course, you might be very competent at algebra yourself, and you may be able to skip out some of these steps. A moment with significant figures. With exams, depends on the paper that you do. So if it's a theory paper, depending on whether you're doing IAL or A-level, papers 1 and 2 at A-level are theory papers. Papers 4 and 5 with IAL are theory papers. You do not need to match your SF to the SF in the question, but you do need to control yourself with SF. So 3 to 4 SF is usually standard for theory paper questions like this. It's a calculation, it isn't based on practical work. Our next one. Japanese bullet train is traveling at 70 meters per second. If the train travels 240 meters in 10 seconds, determine whether the train decelerates or accelerates. Okay, we know it's S, we know it's U, and we know it's T, and we're looking for A. And we will be able to tell from the sign of A whether or not it is increasing or decreasing. So if it's accelerating, we'll get a positive, and if it's decelerating, we'll get a negative. So we need to think about an equation that has S, T, A, and U in it. And you think through your SUVAT equations, or you look through them, if you've got them next to you, and you say, all right, S is equal to UT plus a half AT squared. That has the 4 quantities that I'm after in it. And again, I'm going to speed this up now. You can work away, pause the video, and come back. Turns out it was decelerating. Always a good idea to show as much working as you can. It doesn't take very long, and it keeps you on the right track and makes sure that everyone understands you know what you're doing. Next question. A car has an initial velocity of 6 meters per second and a final velocity of 10. How long does it take the car to travel 128 meters? So get your highlighting your numbers. U, V, s. How long is t? So we need an equation that has u, v, s, and t in it. We mentally click through our SUVAT equations and we say, right, s is equal to u plus v over 2 on t. Next question. An Olympic sprinter crosses the finish line with a speed of 10 meters per second. If the sprinter comes to rest just in front of the advertising signs, which are 25 meters from the finish line, what is the deceleration of the sprinter? And I've highlighted here some other things. So we have, that's going to be our u, 10 meters per second. Rest, you always look out for that because that means we have a v of 0. Or it could be starts from rest, at which point your u is 0. That's 25 meters, so that's our s, and we want a. So again, v, u, a, s. This is our first opportunity to use our final equation. Again, pause if you like, work your way through it. I'm going to speed this up, and you can hit play when you're ready. This is our second last question. Dropped from rest, there it is, and falls 16 meters before hitting the floor. How long does it fall for? Take acceleration to be that. So, our u is 0. That's our s. There's our a, and how long means we're looking for t. U, S, A, and T. U, S, A, and T. Tick, 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 clicking through your equations, and we land on number 3. Pause the video, work your way through it, come back. Final question. And this is sort of a double-barreled question here. We have to do 2 parts. Let's see what we've got. Man is walking along, minding his own business at 1.5 meters per second. A fairly benign terrier chases the man. The man accelerates at 0.5 meters per second squared for 30 meters until the dog gets bored. What is his new velocity? So what are we given and what do we need? There's his u, walking along. That's his a, and that's his s, and we are after v, the new velocity. So that's the first part. So we think, okay, an equation that has v, u, a, and s in it. Click, 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 number 4. Again, pause, come back. Alright, so we found his final velocity. How long did this embarrassing incident take place for? So now we're after t. We have v. So we have some choice here. We can use our original data, we can use our v. We think what is going to be the most straightforward one for us. We want t, v is equal to u plus at, jumps out. Again, pause, work, come back. All right. Over the course of those problems, we have used all of our SUVAT equations. When it comes to, this is your 12 work, so when it comes to the final exams, you're rarely going to get just a single problem with a SUVAT calculation in it. But if you become very competent with these, they get inserted into all sorts of topics. And you get this information and you're expected to use SUVAT equations to find a quantity that you will then go on to use for something else. So if we look back at our specification point, the whole point of this was to be able to use the equations for uniformly accelerated motion in one dimension, also known as SUVAT equations. I think we have shown that we can use them.